All right. Yesterday we did the arithmetic sequences, and there is a second type of sequence that we're going to look at before we leave these things behind us and move on, and that's the geometric sequence. And the difference between the arithmetic and the geometric sequence is with yesterday's sequences there was a common difference. You kept adding the same number, d, over and over and over again. You don't have that with geometric sequences. What you do have is any two consecutive terms have the same ratio. So if we divide the second term by the first term, we get some number r. If we divide the third term by the second term, we get that same number r. The 45th term divided by the 44th term is r. And this r, yesterday d was known as the common difference. R is known as a common ratio. So here's a geometric sequence: 2, 4, 8, 16. When you look at these sequences, it's good to look at the common differences as well. So we look at that first. We have adding 2, but this is adding 4, but this is adding 8. So there's no common difference. The first differences are increasing. So it's not arithmetic. Let's look. 4 divided by 2 would be 2. 8 divided by 4 would be 2. 16 divided by 8 would be 2. So we have a geometric sequence with a common ratio of 2. If we were to find the nth term for this one, you could just kind of reason this one out. These are being doubled. These are increasing powers of 2. 2 to the first, 2 squared, 2 cubed. The nth term here is 2 to the n. In general, though, we got a formula for to find the nth term of an arithmetic sequence, and we're going to get that for geometric as well. And then we go ahead and say of a geometric sequence. What does all that say? It says the nth term in a sequence is equal to the first term times the ratio to the n minus 1 power. 25th term would be the first term times r to the 24th power. One less, right? How does that work? So let's write the first 5 terms of a geometric sequence whose first term is 3 and their common ratio is 2. Okay, so the first term is 3. The second term would be the first term times the common ratio to the 2 minus 1 power, or 1, which would just be 2. The third term would be the first term times the common ratio to the 3 minus 1 power, or squared. The fourth term would be the first term times the common ratio to the 4 minus 1 power, and so on. Let me expand these. So this would be, the second term would be everything that makes up the first term times a power of 2. The third term would be everything that makes up the second was 3 times 2, times another power of 2. Fourth term is everything that made up the third term, which was 3 times 2 times 2, times another power of 2. Everything that makes up the fourth term times another power of 2. And this sequence is 3, 6, 12, 24, 48. Let's find the 15th term, where the first term is 20, common ratio is 1.05. And we want 15th term. 15th term is equal to the first term times the common ratio to the 15 minus 1 power. About 39.6. Good stuff, right, Sarah? This kind of stuff makes your heart happy, isn't it? Better than partial fractions. Law of sines. It's good stuff. Keep doing these. Find the 12th term of geometric sequence 5, 15, 45. Find the 12th. Well, what's really going on in this sequence here? What's the deal there? What's the next term? Or what? How are you getting from term to term? Yeah, it's being tripled, right? So any two terms have a ratio of 3, right? 45 to 15, 3. So we have a common ratio of 3. We have a first term of 5. That's everything you need to know to find the 12th. First term, common ratio to the 12 minus 1 power. Isn't that great? 185,735. Would you love it if the whole test was made up of those? Let's get a little crazy. Sarah wants to get crazy. The fourth term is 125. The 10th term is 125/64. Find the 14th term. Well, to go by the formula, we would need to know the first term, which we don't have. We would need to know R, which we don't have. R is the ratio between any two consecutive terms, and we don't have any consecutive terms. So there's trouble afoot. We need to find, at least we got to find R. That would help. We had one like this for arithmetic ones. I remember that. The one that Mason snapped off. I remember it was 3. Maybe. I can't remember. And then we did it over in a more general way, and we related the two terms that we had, and we used that to find the common difference. So there should be a way to relate these two terms. If we could do something, compare A10 and A4 ... whatever we can find to make that some sort of a true statement. By what? Like we did the difference. Yeah. And how exactly is that R gonna... There is got to be an R in there somehow, but what about it? Just one R? Like that? 6R? Like that? Check out... Where's my... There they are. Check that out. We could do the same. Let's relate the second term to the fifth term in this sequence. To get from the second to the fifth, here was the second, 3 times 2. And here was the fifth, 3 times 2 times 2 times 2. The difference between those two was the 2 times 2 times 2, right? It's not in A to the second, but it is in A to the fifth. So this would be a true statement if we took the second term and multiplied by 2 times 2 times 2. Right? Follow that reasoning so far? So Mason is super close, because that's not 3 times 2, that's actually 2 to the third. So coming back down here, if we just move that 6 and put it in a shrink ray, I think we've got it. Taking another look at this one, you might notice this 3 is the difference between this 2 and this 5, right? And this 6 is the difference between this 4 and this 10. So if we know A10, we know A4, we can find R to the 6, because that'll give us one equation, one unknown. So let's see, A10 was 125/64. A4 was 125. Divide both sides by 125, and you have 1/64. It's R to the 6th. How do you solve that for R? How do you solve it for R, Erica? How do you solve it for R? Tell me. Come up with it. What would you do if it was R squared? What would you do if it was R squared? You'd square root of it. So what would you do if it's R6? Take the 6th root of it. So we need to take the 6th root of both sides. And R would be the 6th root of 1/64. Does the calculator do that? I learned something this morning in second period. I learned that you can actually go 6th root and go math 5 of 64, and it actually does it. And I did not know that was in there. I've never seen that before. Y'all saw that before? Y'all knew about that? Never seen that before. It's funny. I have always gone 64 to the 1/6, which is the same thing. I just didn't know about the other button. I don't know which I like better. I think just to the 1/6, because then I have to go into menus. But either way, the 6th root of 64 is 2, so that would be 1/2. So if R is 1/2, then what? We need the 14th term. Think of any clever way to get the 14th term? Burns, you got any clever ways up your sleeve over there? Come up with one. We just related the 10th and the 4th term. Can't you relate the 14th term to something else we know? How? How's it related to the 10th? R to the 4th. And we know what R is now. We don't know the 14th. We know that the 10th is 125/64. We know that R is 1/2. That is an equation with one unknown that's already solved for A14. And 125/64 times 1/2 to the 4th. Yuck. 125 1024. That was a long one. We should recap that one. Let's see. We were given the 4th term and the 10th term and asked to find the 14th. The only thing that we knew about it is that I said it was a geometric sequence. So that means that there is a common ratio. So we set about finding that common ratio because that's what ties all the terms together. So we related the 10th to the 4th term by figuring out that the difference between the two is 6 factors of r. So if you multiply a to the 4th by r to the 6th, you get the 10th term. Plugged in what we knew, solved for r, and found out that the ratio is 1/2. And then we turned to Burns for guidance, and he related the 14th term and the 10th term, figuring that they are related by 4 factors of r. We plugged in everything that we knew and got the 14th term. What a wonderful test question. That is great. 2 more small details. We did the sums of arithmetic sequences, and we also are going to do the sums of geometric sequences. Simple enough. Simple enough for a caveman. Alright, well, how does this work? It's pretty straightforward. Let's find the sum from 1 to 12 of 4 times 0.3 to the n. That's a geometric sequence because 0.3 is being taken to a power, and that power is increasing in each step. And we can so totally use this formula.
Mr. McGee?
Yes.
I have a simple question of you.
Go ahead.
Where did you put my Outlook?
Start menu.
No.
Yeah, it's at the very top of the start menu.
Okay. You're a dead man, I'm telling you this.
Alright.
Thank you.
Yep. Start menu. First place I always look. Okay, so the 12th term, we're supposed to take the first term and multiply it. So we need to figure out what is the first term. What is the first term of this summation? What is it, Shannon? Put 1 in for n. Yeah, first term, right? When n is 1. It's what? Yeah, times what? 0.3 to the 1 power is 0.3. Nobody's mentioned the 4 though. Yeah, so the first term is 4 times 0.3, right? What is that, 1.2? Okay. Or 1.2. Alright, so the first term is 1.2. 1 minus the ratio 0.3 to the 12th, because this is the sum of the first 12 terms, over 1 minus the ratio. Let's be very careful putting that in the calculator, because you screw it all up if you miss a parenthesis. You could break it up. You could do 1 minus 0.3 to the 12th, enter, figure out what that is, 1 minus 0.3, enter, divide the 2. You could do it in steps. Or you could do it all at once. And you have 1.2 times the quantity. Open the top. 1 minus 0.3 to the 12th, close the top. Divided by, open the bottom. 1 minus 0.3, close the bottom, close the quantity. 1.714. You could try that and make sure that you do get 1.714, although it never happens that everybody gets 1.714 the first time through. So you might want to try that and work out the kinks before we go to the last thing of the day. Did you get it, Sarah? Is it coming around, Courtney? If Amelia was here, we'd know that she got it, because she would be like cheering for Narnia. Sure do miss her. Poor little Narnian. That's right. Okay, we good? Lots of 1.714s out there? Sum of infinite sequences. What? Infinite sequences. Perhaps you're skeptical. You say, how could you possibly add up a sum that never ends? How could you do that? Well, they do kind of end. This works for when r is less than 1. Like a fraction. So you're taking a fraction to a power, which gets you a smaller fraction, which, when you take fractions of things, you're actually dividing. So these infinite sequences do what we call converge on a certain value. So it is possible to take their sum. But it's pretty simple, straightforward formula. Let's take the sum from 1 to infinity. That. Wow. That's pretty scary. Well, sum equals, we need to know the first term. First term is not 0. 4, right? When you plug 1 in there, you get 4 times 0.06 to the 1 minus 1, or 0. Anything to the 0 is 1. 4 times 1 is 4. So the first term is 4 for 1 minus 0.06. 4 divided by parentheses 1 minus 0.06 parentheses 4.25, what was it? Four point two five. That is all there was for today. There is the assignment from the calendar. Also, if you've been checking the calendar, you see that Friday is a test review and Monday is a test. Just throwing that out there. Any days that you miss, there's also, I mean, right there it is. That you can get it from the calendar. Yep. And so the test Monday goes from everything from the last test to this right here, geometric sequences, last thing on the test.